Welcome everyone to ENME 351. This will be our first lecture of the semester. I'm holding this lecture as a video lecture since I'm away at a conference for this particular date, but I'll be back for lecture on Wednesday, and we'll resume our in-class lectures in the lecture hall on Wednesday. And of course, as I'll be talking about here, there will be some pre-lecture videos that you'll need to take a look at and answer a pre-lecture quiz, both available on Elms prior to the in-class lecture. So let's get started. The plan for this lecture here, we'll introduce the course. We'll talk about how the course is organized and what you can expect this semester. And then we'll also briefly introduce the labs, both the kit, and we'll talk briefly about the Arduino and the software, just to give you an idea of what I'm expecting from everyone in terms of labs and hardware and software for this semester. There's a homework due. We have homework due this Thursday. It's homework 0.1. I call it my speed dating homework. It's me getting to know you, what you're interested in, and what you're expecting from this course. And usually I'll use that such that I can tailor the course so that you get the best experience for your investment this semester. So homework 0.1 is due Thursday at 11:59 p.m. and you'll submit that on Gradescope, and I'll talk more about that here briefly. And then I also want to bring to your attention Lab 0, which is effectively purchasing or acquiring your Arduino and the associated hardware for the Arduino and the components to build the circuits for this semester. You want to go ahead and get that completed, get that acquired ASAP. A little bit about me. I am an alum of the department, a proud alum of the University of Maryland Mechanical Engineering. After undergrad, I went to work in industry for several years and then left to go back to grad school at the University of Colorado. After grad school, went back into industry, served as a director of a mechanical engineering branch, and eventually started teaching and fell in love with teaching. And now I'm here full-time teaching as faculty within the department. My engineering and research interests are primarily in the fields of laser remote sensing, both from airborne platforms as well as ground vehicles, such as autonomous vehicles. So I've done most of my work in airborne laser remote sensing over the years. And then from a mechatronics standpoint, relative to this class, primarily building electromechanical steering systems for optics and lasers of a different variety. All of which is used to provide something like a 3D map of an area that you're flying over, or a 3D map of the scene around the car, let's say, as you're driving an autonomous vehicle down the road. With that in mind, here's my plug for my tech elective, ENME 49Y. This is a remote sensing course where you'll dive deep into the underlying physics of various remote sensing systems or sensors, such as LiDAR, radar, and computer vision. You'll get to work with the Raspberry Pi plus the camera, and you'll learn some Python along the way. You'll get to do things like computer vision algorithms for tracking of objects. So here we're tracking a green tennis ball. You'll take that code that you developed and then integrate that with hardware to build your own LiDAR sensor and go out on campus and actually create a three-dimensional map of the target of interest. So here's a student from a previous semester who was really interested in mapping the testudo in front of Xfinity. So as a part of the class, the student built his own LiDAR sensor, a computer vision-based LiDAR sensor, and went out and created a three-dimensional map, as you see here, of testudo. So let's talk about this class, ENME 351, Mechatronics. You're probably saying, Mecha what? Well, this is Mechatronics, right? This is a course at the intersection of mechanics or mechanical engineering and electronics or electrical engineering. It's really the combination of the two. Let's take a look at an example of a mechatronic system. And if you can, turn up the sound on your laptop, your iPad, whatever you're listening with, and really try and listen to the sounds of this mechatronic system as you're watching the various components of the system translate across the screen.
Come closer. Okay.
Yes. Close hand.
Did you say close hand?
Yes.
Okay.
Full speed.
Okay.
Rest.
Did you say rest?
Yes.
Okay. Okay.
Close hand.
Did you say close hand?
Yes.
Okay. Come closer.
So this is a mechatronic system, or in this case, a robot, a humanoid robot, that's developed by a group called InMove. And InMove is an open source platform. So if you're interested, go over and Google InMove. You can take a look at all the parts and all of the schematics for this particular mechatronic system. Mechatronic systems are becoming ubiquitous with most modern products or devices that you would purchase or use in your everyday life. Most products have some type of microcontroller buried inside the product, and that's used for sensing and command and control. So 1971, this term mechatronics is officially coined. So it's that intersection again of mechanical engineering and electrical engineering. Complex systems have many different microcontrollers. So here we have a BMW, right? Has over 60 different microcontrollers, each responsible for different subsystems of the automobile. So here's a working definition that comes from a 1989 paper by Dinsdale, right? It's this integration of mechanical components with electronics and intelligent control. It's this integration, or one could say intersection, again, of mechanical engineering and electrical engineering. With this definition in mind, let's go back then to the InMove system, right? So this is a robotic system where the microcontroller is controlling different inputs and outputs to facilitate different maneuvers with the robot or to perform different functions. So this intersection of hardware and software, you see here we have something like servo motors connected to linkages, maybe something like fishing line, for example. And those linkages are controlling different components of the robot, let's say the fingers or a hand, some sort of joint, when these electrical intelligent control signals are sent from one part of the robot to the other. Take a look at this mechatronic system now, and once again, turn the volume up so you can really hear the components actuating as the mechanical components are translating across the screen. And it'll be interesting to see what your initial reaction is to the video, and then as the video comes to a conclusion, what you think about the system.
Fă ceva semne. Mișcă-le pe toate acum. Se vadă așa, se vadă asta așa. Asta așa.
I always love to play this video during the introductory lecture for this course, because when you first view the video, you could probably convince yourself there's a human hand underneath this glove. And then as you pan out in the video, you realize, oh, actually, there's different servo motors that are being actuated via linkages, in this case, fishing line, to extend or curl each finger independently. And then as the video continues, you realize, oh, there's actually an operator here with a glove, and on each finger of the glove is a sensor, in this case, a strain gauge sensor. And it's really that input signal, that sensing from the user's glove, as recorded and as controlled by the microcontroller that allows the system to output some sort of signal to the servo motors and actually open and close the robotic hand. In terms of the course map for this class, here we are up here with ENME 351. That's the class for this semester. And in terms of prereqs, it's my expectation that you have a understanding of your physics courses as well as ENME 350. That was Electronics and Instrumentation 1, or effectively analog electronics, right? So ENME 351 is really all about digital electronics and mechatronics, but you need a solid foundation in physics and your analog electronics courses in order to be successful in this class. And looking ahead on the course map, I'll also bring to your attention ENME 462. That's effectively going to be an introduction to control theory, just so that you're thinking about this during the semester. All of the material, all the op amps, and all the different components you're studying this semester will really all come together in controls to try and control something like here we have the inverted pendulum. In terms of structure for the course, there is an in-class lecture every Monday and Wednesday, and that's a 50-minute lecture where we'll get together and we'll talk about various topics related to mechatronics. The notes for each in-class lecture should be available on Elms in advance. That's why I say hopefully here. But all the notes will be available on Elms. There is a homework assignment roughly weekly. I think there's about 11 or 12 homework assignments this semester. Once again, available on Elms. However, they are submitted on Gradescope. Talk more about that in a second. There's a total of 9 labs, so you're looking at roughly every week to have a lab assignment where you'll meet in the lab and you'll demonstrate or work through various aspects of the lab. And then there's 2 exams. There's 1 midterm and 1 final. All of the details for the course structure, including grade breakdown, contact information, and a schedule for the semester is available via the course syllabus, which is also available on Elms. There is no one single book that really covers all of the information that we will discuss this semester. Because this course really is an intersection of mechatronics and electronics and software for control, it's difficult to find one book that covers all the topics that we'll cover this semester. So here is sort of a smattering of books that I pull information from to generate slides and material for the course. And I would definitely recommend, if you can, to have these books available as you're going through the semester. Everything you need, quite frankly, will be provided in the notes. But if you want to get into depth in a certain topic, these are some great references for you to read additional material. In terms of the grading policy, here's the breakdown. We've got 10% of your grade for the semester based on homeworks, 10% for these pre-lecture quizzes. Talk more about that in a second. 15% for that midterm and 25% for the final exam. And then 40% of the semester grade is based on the labs. So this is a really hands-on, lab-oriented course. And as a result, the majority of the semester grade is based on the lab grades. And just to bring to your attention, if we look at the homeworks and the pre-lecture quizzes, I'm going to go ahead and drop the lowest 2 grades for each. So I'll drop your lowest 2 homework scores and your lowest 2 pre-lecture quiz scores because you know what? We're all human. We're all prone to have a rough day here or there. So I'm no different. And as a result, I will offer to drop the lowest 2 grades for homework and pre-lecture quizzes. Okay, I want to be very clear about the statement that I'm presenting here. You, as a student in my class, are my number 1 priority. Here is what I try as best I can to avoid in all of my classes. I view myself as the teacher, as an educator. It is my intent to do the best job possible to provide a very high value course throughout the semester. Now, the reason I bring this to your attention is please use me as a resource, right? Anytime throughout the semester, if you feel that you're not getting something you need or you would like more, just come talk to me, make an appointment, swing by my office. The point here is anytime you need something throughout the semester, please use me as a resource. You are my number 1 priority. I also want everyone to keep things in perspective. I know how the semesters go. I know the roller coaster of emotions that students go through because I am an alum of the department that you are studying in now. So keep things in perspective, right? This is my student happiness curve. And this happens every semester with every course I have taught. And this happens in all courses, in my opinion. So you'll notice the y-axis is sort of student happiness, smiley face. X-axis is time. And usually we're starting off at the beginning of the semester. Everybody's very happy, excited about the class, excited about learning. And as we go along, sometime, maybe around the midterm exam or some of the labs or whatnot, that tends to decrease, right? And of course, there are no units on the axes, but you get the general idea. And as we go along through the semester, we sort of work our way up to the end of the semester. And the goal here is that we end the semester happier, and we've had a overall positive experience, and we've acquired a new body of knowledge throughout this journey. But just keep things in perspective. I know how it goes. I understand it. And as with the previous slide, again, anytime you have any concern, feel free to come talk to me at any point in time. So last bit about course structure then. This is a flipped classroom. And if you haven't heard of a flipped classroom before, that's fine. That's great. I'm excited to bring that to you. In a flipped classroom, a very traditional flipped classroom, you will basically have a lecture at home, something like a video or audio or whatnot, the night before or the nights leading up to lecture. And then you come to lecture and you would do nothing but exam problems or homework problems, or you'd actually put that knowledge to use. So the way I teach this class, it's sort of a flipped classroom, semi-flipped classroom. We'll have some lecture videos beforehand. You have to take a pre-lecture quiz, very short. They're all at most 2 questions. And then when we come to class, we'll have a quick review, and then we'll get into some problem solving, right? And it'll be very interactive. We'll work as groups. And I'll tell you right now, most of the in-class exercises are old exam problems. So it's a great way to practice and get ready for the exams and to sort of most efficiently use our in-class lecture time. So the flipped classrooms work really well in previous semesters, and we'll continue that this semester. So here we have the lectures and notes and quizzes on Canvas or on Elms. So you're going to watch the video lecture. You're going to take the pre-lecture quiz. If you have any questions or comments, we'll talk about Piazza here in just a second, but get on Piazza, make a post. Everyone in the class gets to see it and has the opportunity to respond. And then when we get together in class for lecture, I'll do a brief review, maybe 1 or 2 slides, and then typically we'll get into some exercises so we can actually take that theory that we just learned and put it to practice. So with that in mind, let's take a look at the Elms or the Canvas site for 351 this semester. Here we are on Elms, and I'm in student view. You'll notice I have a student view, leave student view here at the bottom. And this is my attempt to provide a legitimate example of what you should be seeing when you log in. But when you log into Elms, you should see here on the home page, and you'll see the navigation panel on your left. And I've tried to minimize the buttons in the navigation panel just so that you have just the information that you need for the class. The most important button I'm going to tell you right now is modules. Everything you need in the class is driven by modules, right? So if you go in, you'll see there's an introduction and logistics. You can click on, here's the syllabus for the course. Here's the grade scope entry code, which you'll need to actually enter the course. And I'll talk about that here in just a second. But let's click on, say, Lecture 1 module. You see for this module has all the information you need for this first lecture. So here's the slides. This will be the slide deck that I've covered in this video, and I'll give you the annotated version. Typically, I'll give you a blank slide deck such that you can work through the problems and take notes on your own before class, and then after lecture, I'll give you the full annotated slides so that you don't feel rushed. Did I miss a bullet here or there or whatnot? I will tell you, however, that I do not post solutions to in-class exercises. Right? That is sort of my way of motivating students to be engaged in class. And since they're old exam problems, it's a good way for you to have some skin in the game, let's say, to really work through it and then get the solution in class such that you're prepared for the exam. So we'll go through the solutions in class to the in-class exercises, but I won't actually post the solutions. And then we also have some things here. I usually will post fodder or other, if we go to the next lecture, old examples of student projects, things that I think are relevant to the lecture and the topic that we are covering. So when you get to Elms, everything you need is in the module section. So you go through modules. We also have assignments here. So the assignments will be the homework assignments. So we have a pre-lecture quiz for lecture on Wednesday, and then we have a homework assignment, right? So I call it the speed dating assignment, and you can get the PDF of the assignment on Elms. You'll actually submit that on Gradescope. So let's take a look at Gradescope then. When you log into Gradescope, you'll have to sign up for the class. So the entry code is up here at right. There's an image of that in the modules section of the course on Elms, but you'll log in and then you should be able to see the homework assignments that are due. So right now we have one homework assignment, 0.1. Click on that. You'll be asked to submit or upload a PDF. And then it's very important, make sure that you tag the pages of your homework assignment to the respective parts of the assignment. So if there's 4 problems in the homework assignment, and you have homework, if you have problem 1 on page 1 and 2, make sure you tag in Gradescope. Page 1 and page 2 actually have the response to problem 1, and 3 and 4, problem 2, and so on and so forth. So that's the assignments. We do have pre-lecture quizzes, so let's take a look. So Wednesday, we have an in-class lecture on digital signals and digital logic. So before you come to class on Wednesday, you need to watch the videos. They're each pretty short, typically less than 10 minutes. This is the pre-lecture video. You're going to get mostly theory in these videos. And then you'll go up here and you'll complete the pre-lecture quiz. And this is, I think, 2 questions. Should be relatively straightforward to solve, but just to give you an opportunity to exercise the theory that you just learned and really get prepared for the in-class lecture. So when we come to class on Wednesday, you will have viewed the videos, taken the quiz, and you'll be ready to rock and roll with the in-class lecture slide deck for that particular lecture. And you'll notice here the in-class lecture slide deck is posted right here. So in-class lecture. And this is just O2, and I'll give you O2-AN for annotated version. I'll give you that after Wednesday's lecture. And then last thing I want to discuss, we have Piazza here. Piazza will be my preferred means of communication for the course. So I would prefer all email go through Piazza. That helps me organize things, make sure I don't miss anything. If it goes to my school email, that's usually flooded with various information, and it'll be, quite frankly, be a lot slower for me to get back to you. So if you make sure you log in, create an account with Piazza, you'll see all of the posts, and anytime you need to contact me, you can make it a private post. Only I get it, or you can make it public, and therefore your colleagues in the class will often have a better opportunity to respond if, say, it's late at night, right before the homework is due. All of the students in the class have an opportunity to respond. So it's a great tool for the students, and I've used it with success in previous courses, and we'll use it again this semester. A reminder then that all homework will be submitted via Gradescope, and myself and the teaching team, we will grade and return your homework via Gradescope as well. So head over to gradescope.com. You have the entry code here, and make sure you can access the Gradescope class, and make sure you complete homework 0.1 by 11:59 p.m. this Thursday. Pretty much every week, homework will be due by midnight on Thursday, so by 11:59 p.m. each Thursday night. Okay, let's take a look at the course outline. Here's a very high-level outline for the course, but I like the summary nature of this slide. So the course starts with digital logic. We'll talk zeros and ones. We'll talk other number bases. Then we'll get into microcontrollers. From there, we'll get into signals and sensors, right? We're going to always be sensing some signal with some sensor. Then we'll get into signal conditioning. So there we'll talk about things like filtering, for example. And then we'll get into actuation. So how do you actually actuate something like a pneumatic valve or a servo motor or a DC motor? And there's a nice flow here from digital logic, which we'll be talking about this week, all the way down to actuation, which we'll be talking about the last 2 to 3 weeks of the semester. Here's another way of looking at the outline of the course, a little more detailed here. We looked at this video here. This was a nice example of a Mechatronics system where you have an input sensor, like a strain gauge on the operator's glove. You have some signal conditioning electronics here, maybe voltage divider, and that's getting read into a computer or a microcontroller using something like an analog to digital converter. So you have these signals coming from the environment through a sensor, getting conditioned, and ultimately getting converted to a digital signal, right? These microcontrollers, they talk in the digital domain, zeros and ones. And then on the other side, we had some actuation occurring. So the microcontroller is going to be generating some analog signal, right? It's going to be converting a digital to analog signal through a DAC. We may condition that again, we may not, and that'll ultimately be used to drive a transducer or an actuator. So here we have servo motors that are being driven by the signals coming from the microcontroller, and then there's some mechanical linkages to actually curl or extend the fingers of this robotic arm. So I like the flow here of this course outline. All of the arrows in red, those are our signals, and we'll be diving into much deeper detail about each section of this process throughout the semester. So to start wrapping up the lecture here today, we looked at the in-move mechatronic system. In this case, it was a humanoid type robot. And we looked at another mechatronic system where we have a glove that's being driven by a user, by an operator, and that's effectively controlling a robotic arm, in this case, a robotic hand. So you should be asking yourself, okay, I've got some sensing, some input, and then some actuation or some output. So what are the sensors that you see here? Well, in the glove, we're going to have something like a strain gauge or potentially a potentiometer that is going to provide a change in resistance, which if we use something like a voltage divider will give us a change in voltage, right? So that'll give us that input signal. The actuators here, mostly servo motors. There might be other types of motors or other different actuators, which we'll talk about later in the semester. But that's really the output signal coming from the microcontroller and actually outputting or affecting or actuating something back in the environment. And then we have this notion of computation or control. So there's something like a computer, or for this class, we're really going to be talking mostly about microcontrollers, specifically using the Arduino, which is actually not a microcontroller. The Arduino Uno has 2 microcontrollers on board, right? 2 Atmega chips. But we'll be talking in depth about the Arduino and using this for the computation and control, using for this some of this logic, taking these inputs and providing these outputs, and how you can control things like a servo motor. So we actually have a servo motor lab that we'll work through this semester. With that in mind, I do want to urge you to go ahead and acquire your parts for the Arduino and the parts kit. I think it used to be called the Sidekick Kit in past years. It might just be the parts kit now. But the components can be the same, and I can provide a list of the components that are that you're being expected to have in your possession for the labs. But you want to go ahead and do that ASAP. I will put some instructions up on Elms. It'll be under the Assignments tab, so look for Lab 0. You know, the prices fluctuate over the years, but you're looking at something on the order of $50 total for all these components. And then lastly, I wanted to bring to your attention this notion of simulators. There's a great variety of simulator tools that are all online that can be used this semester. So almost anytime you're building a lab, you should think, okay, I understand the requirements for the lab. Let's see if I can simulate that. Look at the performance that I'm expecting, and then actually build a circuit and see how well your physical circuit meets that expected or simulated performance. I will bring to your attention right now Lab 9, the project lab. This will be the last 2 weeks of the semester. This is worth 200 points, so it's effectively 20% of the total lab grade, the total lab grade being 40% of your semester grade. So it's a significant amount of points. It's a significant component of your grade, and it's really been a great opportunity for students to show off their creativity and the skills and the knowledge and the theory that they've learned throughout the semester. So there's plenty of examples if you'd like to view examples of videos from past semesters. Head over to my site, oneshell.org. I'll also be posting in just about every module on Elms 1 or 2 previous projects from students from prior semesters. So it's a great way to take all the material that you've learned this semester and sort of put your spin on it, your creative spin, and demonstrate something for the teaching staff at the end of the semester. So with that, we'll go ahead and wrap up today's lecture with the course outline. This is an introductory lecture today, so we'll start with digital logic on Wednesday. Just a reminder to view the pre-lecture videos, answer the pre-lecture quiz, and then bring the slide deck with you to class. You can print it out, put it on your iPad, whatever you prefer. But we will meet in class on Wednesday, 10 a.m., and we will continue our exploration of all things mechatronics.